Sorry about that. That just takes a moment to set up, but that's the idea of grabbing these things. Okay, so we've got two, we've got Khalids, and we've got omids. That's fantastic. Okay, Khalid, thanks very much. We'll start with you here. In terms of this is just to discuss this assignment. I've got the solutions of this written up. I will, just after class, I will post this as a web page to the course shell so you can sort of compare your solution to this solution. But here we go. So the first bit is pretty straightforward. We're going to import NumPy. That's fantastic. And I talked about downloading the file. That worked out okay. Okay, so let's talk about this right here. What's going on in this question in this code?
Yeah. So
Khalid?
So basically, in the previous command, you can see that I have like downloaded this, downloaded the file, and in this following command, I am just loading it to a variable that's called the data, and all the data will be stored here, and I'll be manipulating and using that variable in the later stages of this assignment. So all the data have been loaded into the data, and data.keys just give me a like what kind of data is it? So it's saying that it's some sort of an object right now. So
okay.
So in summary, it just loads the data in the variable.
Okay, so I'm just gonna execute some of these lines. Hopefully they'll just work on my system. There, download the data. So let's do that. And great that you get a key view. That's the data, and it is an MPZ file.
Right.
And I get that data.keys gives you a keys view, but as you figured out over here, this is a way of actually seeing what the keys are. Right? So I get that you've correctly extracted out the data, but if I was to run this, nothing appears. So
like basically we have to like pin the like we have to like put the T or S, whatever variable you want to like extract the full data. So,
right. So I would suggest that rather than this line, right, you probably wanted something like that.
Yeah.
Right, just so you can see it. Now, you obviously must have done that to figure out what the T, S, and P, but it disappeared from the solution.
For the better view,
Okay, so the way of using this NPZ file, right, which is just a NumPy compressed file, is to sort of get the file, and then to know what's inside of it, you have to open it up and inspect it, right? You have to sort of take a look at the file before you start loading it.
Yeah.
Right.
I should have kept the inspection commands as well.
Yeah, it was just in terms of going, like, I know you must have done it, but in terms of doing it. Okay, so I'll ask you one more question, which is, so I see these three lines are loading data you're loading data into the T, S, and P variables, and then you do these three lines. So what's the difference between these three and these three?
Yeah. So basically, initially in the THP variable, I'm loading the whatever data is in the CHP, and there might be some invalid data in that CHP file. And in the later three commands using this max function, invalid, I am like cancel out all the invalid data. So all I have is now data without invalid ones.
Okay, so there's something about how the code is written, which is these three lines, you're attaching them to these three variables.
Right.
And then you overwrite those three variables.
Exactly.
So these three lines aren't needed.
Yeah, I'm not using them.
Right.
Like, later.
You're not using them. So either what I would do is do a block like this and then say, like, that makes sense. If you wanted to do something like that would be a meaningful way of doing it, and then whatever the third one is. So that makes some sense in terms of you're loading it, and then you're masking it. And the advantage of doing that is then you can actually see what the data looks like, and you can compare that to what the mass data looks like. right? So it's this idea of loading it in. Alternatively, the other way of doing it is just that. So can you see how, like, it's just clarity of code, right? So think about an operation, you're bringing the data in. Well, if you bother to load it, use it, right? So I would go this way or this way, not both. Right. Anyways, fantastic. That's great. Okay, so Omid, let's flip over and just compare what you've done. Okay, you did exactly what I recommended. That's fantastic, right? You've loaded the data. It's all good. Okay, so here's some data. My question to you, Omid, is you masked the data here. Why didn't you bother masking the data here?
Yep. Sorry, could you repeat your question again?
In question 4, you loaded the data and then you masked it.
Okay.
Here you loaded the data, but you didn't mask it. Why didn't you mask it?
Yeah, this is something that I forget, and maybe I didn't get the question exactly. Yeah, okay. You're right.
No, well, I'm trying to trick you, Omid. Why did we need to mask this data?
Okay, because we may have some invalid values in TSP, so that's why you may just there are some invalids such as nan infinity or something like this, so we mask them. Right. But maybe we didn't have such values, such invalid values in date lat and the latitude and altitude of and the levels. Yeah,
that's right. That's right. So that's exactly correct. So what I typically do is, okay, I gotta run your data here. Oh, NumPy's not defined. I forgot. I got 2 different notebooks. But this will let me at least right? So you can sort of see the data. And sometimes what I like to do is just sort of throw a few of the variables down, just so you can sort of see what date is or what level is. Right? It just lets you do that inspection of the data to see whether or not there are any nans or not. So don't, and this is not the assignment, this is working with data, right? When you load in data, especially data you're unfamiliar with, I encourage you to take a look at that data or make a plot of that data. And just think about why you'd need to mask data or not. But that's exactly what I was looking for. Okay, let's ask this question. Okay, here we go. Note the shapes of TSP compared to the arrays. How do those line up? Okay, so Omid, I see that what you've done is you put down t.shape, s.shape, and p.shape, and you put down date.shape and lat.shape and lon.shape. Mm-hmm. Those are the shapes. But I want to ask you this question. What do they mean?
Well, TSPR as the same size. The size is exactly the same for TS and P.
They are the same.
But, yeah. And the date, latitude, and LON, I think here, latitude is, they have the same shape, but it's not clear that number of columns or number of rows are the same in lat, date, as well as altitude, I think here.
Well, you don't have anything about altitude. What you've shown is you've shown the date, the latitude, and the longitude. And each one of those have 75 numbers.
Yeah, but it's not clear that 75 is the number of columns or the number of rows here.
Well, but you know that right here. Here's the 75.
Yeah, so if we just based on T, S, and P, we can infer that. Yeah,
that's right. Right. So this data, and this is one of the things about data and interpreting it. This array T, right? If we just take a look at T, okay, I agree that it is 78 rows and 75 columns. But I don't know, just because of the array, what T refers to, right? What do the rows mean? What do the columns mean? There are 75 columns, and I see that there are 75 dates. Okay, so Omid, we were talking about how you can tell the number of rows versus columns, and I agree that with this way of storing the data, it's actually a bit difficult. 75 refers to the number of dates, latitude, and longitude. Let me explain a little bit what this data is. So an Argo is a vertical float, right? So it's a thing that's out of the ocean, and it's drifting around, and every time it takes a measurement, it happens at a particular day and in a particular location, a latitude and a longitude. And what a measurement is it goes quite down deep, about 2,000 meters, and comes up to the surface and transmits its information. What do you think 78 refers to? If date, latitude, and longitude is the when and the where of a measurement, what's the 78?
It's number of samples, I think.
Number of samples, okay. I would use a slightly different word.
It can be number of just visiting something, for example, number of, I don't know.
Yeah, well, so
yeah.
There are 75 dates, 75 latitudes, and 75 longitudes. What's the 78 refer to?
As I said, it's 78 is referred to the number of samples, but I don't know.
Right, we wouldn't say the number of samples, right? So we'd say the number of dates, the number of latitudes, the number of longs. The 78 refers to the number of levels, is all I'm getting at. Right, so you're taking the vertical profile. Okay. Imagine you're in the ocean, and the surface is level 0, and as you go deeper, it's level 1, level 2, level 3, level 4, down to level 77. So the 78, right, this levels thing has 78 values. And so what every row in this data set is a vertical profile, right? So this is just the depth information that you're measuring the temperature, the salinity, and the pressure on. So when you answered here, the shape of dat, lot, and long were 75. The other piece of information we needed here was levels. And so we can conclude is the rows of T, S, and P refer to the levels, which is depth, and the columns to the date, latitude, and longitude of the observation, right? So something like that. That's how they line up. Does that make sense in terms of understanding what this data is about?
Yeah, as you mentioned, so we can infer that 28, we have 78 number of observation.
Yeah. Well, we have 78. So sorry, there are 75 observations. An observation consists of a vertical profile. It's sort of, in atmospheric science, it'd be like taking a weather balloon and sending it up. It's one sample. The sample's just taken at 78 different levels.
Okay.
Right. So there is a little bit of trying to understand what this data is and what it looks like. And even if you didn't understand it here, by the end of it, hopefully we will. Okay, that's fantastic. Let's go back to Khaled for a moment and just keep on plowing through this kind of stuff. Khaled, same comment. Note the shapes. How do they line up? You've just given me a bunch of shapes, but you didn't actually tell me anything about what that meant. Right?
One.
Yeah. Okay. Load the necessary package plot for doing pipe plot. Okay. So this is great. What's this?
So basically, I'm importing the pipe plot from the matplotlib library. Yeah. And then I'm using that library to plot some data.
Right.
And have a visualization.
But what's this line? But why have you put in matplotlib inline in the code?
I'm not 100% sure what is it, because I got it from the NumPy reference.
Okay.
And that was being used there. So yeah.
Okay. So
I'm not quite sure.
Right. So one of the skills that I'm going to try and encourage you to do, not just for this assignment, but in general, is don't just take random lines of code that they're magic, and put them in, right? That the idea is to read the documentation and understand what the lines are do, right? So if you got a line like this and you're like, I don't know what it's for, read up on it, do a search for it, look at the documentation, try and figure out what it's there for. Right? So don't just type and copy and paste. That's not a great way of learning coding or doing analysis at all. Okay, so I explain what it's for. In older versions of Jupyter, we talked about matplotlib backends, the fact that you can just render to different, you can render to files, you can render to graphics engines, you can render to different things. Inline says, matplotlib, I want you to render and then display the plots right inside this value. In versions of Jupyter made in the last 3 years, this is actually the default. So you don't need that anymore. Where I'm going to say it's important. So if I do a matplotlib, and let's just give you a, let's run that line. I don't have it. Why don't I have it? Let's put it back in there. Conda activate, because we're going to need it. CMSC6950, conda install matplotlib. I just don't have it in this environment. What this line is doing is saying display that embedded inline in the document, right? As a document. You don't have to do that, right? You can go to a different backend so that you can just save files and not render anything. There's another backend which is available, which is the backend notebook. Okay, so this notebook is a different backend which is supported within the Jupyter environment. And as soon as this loads, I will demonstrate what that does, but it might just take a moment for it to come back. But what you're doing is you're choosing the backend for matplotlib. Okay, let's ask you a slightly more interesting question. Okay, so here's one where you have to sort of use matplotlib. So the vertical scale is the levels data. We talked about levels being where you took data. What I want you to do is make a plot so that 0's at the top, 77's at the bottom, and you're plotting all the way through. So you have a picture, and this is great. So what we're looking at here is the fact that in the ocean, near the top, it's warm. And when you get down deep, it's cold. Salt content is actually a little more interesting. Depending on where you are in the ocean, it actually can get saltier as you go down, and then less salty. It can change. Pressure increases with depth. So generally what this means is as you go deeper and deeper and deeper, the pressure increases because of the weight of the water. In terms of your code, what does that block of code do? What does subplot to grid mean?
So basically, for the plot, first of all, I am defining an area using the plot the figure function that is a 12,8.
Yep.
And inside that figure, I am defining spaces for 3 different plots, and that's like the subplot to grid. and that's one. And the first parameter would be the shape, and then the location where I want to put that thing, and then the row span, how much it will span.
Okay. So does row span have a default? Like if you didn't have that, do you need this argument is my question. I don't think you need that argument.
As far as I can recall, as far as I can, it's optional. It's optional.
It's optional,
just
right?
To like,
so it's there because you could have a grid
more wider.
Yeah, but the default is 1. So you normally wouldn't put that in there, okay? So subplot to grid is a way of doing fairly complicated grids, but try and use it a little bit simpler. Okay. Okay, so here you are setting the X lim and the Y lim, right? So these are the limits. How did you choose the limits?
I'm keeping the plot here.
Yep.
So the inversion is happening here. So basically what X lim and Y lim basically does is that you can like set or get limits for X-axis and Y-axis. And if we like pass the maximum value in the axis as the lower limit and the maximum value as the minimum value in the axis as the upper limit, you can get a reverted axis here. So there are multiple. I saw there are 2-3 ways to flip this.
Very good.
Axis, and for some reason I couldn't flip it with the easiest one. That's the inverted. I don't know why it was not happening, so I had to like choose this one. But yeah, there are 2-3 ways to like flip a plot.
Yeah, I happen to like this one. So just a comment about how you've done it. There's nothing wrong with this, but often people, rather than doing everything with this one command and everything with this one command and everything with this one command, I would point out that there's another way of ordering this code. Right? Can you see how that's everything to do with the first plot? Right? So this is another way to think about your program rather than doing all the commands that are the same. And the benefit of this is if I needed to go and add a 4th plot, right? All I'd have to do is copy and paste that entire block. And then just change the 2s all the way through. Rather than having to add a line to the end of this block, the end of this block, the end of this block, the end of this block. So just in term, and then you're sort of seeing this is actually beginning to become a bit of a function that we want to do it. There's something I want to point out though in terms of how you structured this. Imagine you were writing the code and somewhere along the line you made the decision to change the limits here. The way you've written it, you'd have to change the information here, change the information here, and change the information here. So let me, I think I can load in matplotlib now. So I can, we can demo this notebook bit. Oh, whoa, that's weird. No, get rid of this, that's what I need. Oh, it loaded, but then it crashed. There's something wrong. I won't worry about that right now. Okay, what I want to point out, load all the data, James. Don't only load half the data. Okay, so d. Okay, load all the data. So there's another way of using these commands, subplot.grid, which is to share an axis. So rather than, like, you actually get all these different options. One of them is you can share an axis. So you can say share y equals ax plus 1. And what that will mean is whatever you set, share x. Yeah, y. whatever you set this axis to, they all should have the same axes. And so what I typically would do is say to these things, you know what, I want the same axes for all three plots, and they should all share the same axis, right? So you see it says 0 to 70, 0 to 70, 0 to 70. They're all the same. That's because they all are sharing the same axis. And the reason you want to do that is so that if you had some graphical backend that lets you zoom into a certain region, all three of these plots would zoom in together. And that's what this is supposed to do for me, but it's not doing it right now. So there are ways of linking these things together. That's fantastic. Let me flip over to Omid and just see if it's the same solution. Oh, there you go. You used a different version of that command, subplots. It doesn't matter which one you use. They're both great. Fantastic. Oh, and you figured out how to use the invert axis option.
Yep.
Cool.
Yeah.
What I like about what you've done is you have an array of axes. So I want to just contrast the two options. So in Khaled's work, he's got a variable called AX1, a variable called AX2, and a variable called AX3. But if there wasn't 3 plots and there was 30 plots, there's a lot of typing going on. Here, we're going, okay, it's a list of axis options. So that allows you to make your code a bit cleaner, a little more compacted all the way through. Okay, let me ask you this question, Omid. We want to compute the mean and standard deviation of this data. Okay. Omid, this tells me you are a programmer in another language. You know how to program in other languages, don't you?
Yeah, that's right.
Yeah. Okay. So this is how you would have to do it.
Using MATLAB as,
yeah. Okay. Yeah. So this is how you'd have to do it in lower level languages, but it's not what you need to do in a higher level toolkit like this, because arrays know about rows and columns. There's no need to iterate through all of the levels. This internally is a for loop, right? What you're doing is you're looping through, and then you're loading in the index of each one of those rows and columns, right? So it will work. Like you'll get some answers, but you can do a little bit better in the sense of you can take NP mean of T, and as you know, if I just take the mean, let me go back. I must have not loaded it correctly. Oh, there's a mistake. MA and T. This should be a TMA, shouldn't it? Do you see why it needs to be a TMA, not just a T?
Yeah.
Yeah. Okay.
There's a mistake here, yeah.
Yeah. Well, that's what we find. Okay. I obviously didn't run the code. Okay. This is totally subtle, but capital T, capital S, capital P, capital T, capital S, lowercase p. That can make life difficult for other coders. Consistency. Okay, so that works. And I can also take the mean, and you know I just get the average. But what I want is the mean at each level. For any new function, get into the habit of looking at the documentation. So if I'm in Jupyter, and I'm just, my cursor is right there, if you were to do a Shift tab, what you get is the documentation of it right there. And if you did Shift tab twice, you get a bit more documentation. And if you did Shift tab, Shift tab, Shift tab, you get even more documentation. And 4 Shift tabs actually makes the documentation appear down here. So you can sort of see what this function does. And when the function does, it says, take the mean of this array. But then you got these optional axes. And it says, take it along a certain axis. And this axis is just an integer, the first, the second, the third, or the fourth. So if I'm taking it along the 0th axis, what I'm getting is I'm getting a bunch of data where I've taken the average along the first axis, okay? So what this is meaning is I am taking the average along all rows. So for every column, I'm taking the average of all rows, which is why I end up with 75 different values. So this is the average temperature over all depths at any location. That's not what I want. What I want is the average temperature over all observations, all times, all locations, for all depths. And so that's the second axis. And so this gives you data, which is got 78, which is the mean in the number of temperatures. So what I would do is I would do that as opposed to this. Now, you're right. Your code is correct. But in terms of using the library, this would be how we typically would do that using NumPy.
Yeah, this is more Pythonic.
My Pythonic, exactly. And that's what we're trying to go for. Okay, and now you have your own plot, which is the graphs. And you can see that what we're dealing with here is temperature as a function of depth, which is what these levels are. Okay, so I'm going to ask you a question here. Up here, the data went from 0 to 80, right? Why is your plot only going from 45 to 77? Where's the data?
Yeah, I tried to figure out what is the problem here, but I couldn't find out why it is shaped like this.
Okay.
First, at the first glance, I first thought that there may be some data that are nans or something like this,
Yep.
but I didn't think that.
That's exactly right. There are some data which might be nans. Remember how originally you had this? You weren't masking your data. If you mask your data, right, and then run that plot, oh, it's not loaded. Okay, I guess I got to load it. There we go. You'll see that you got the full curve again, 0 to 80. See that? So the error was you had masked the data, but then you weren't actually using the masked array.
Yeah, I forget to use that. Yeah, that's
right.
That's the problem.
That is exactly the problem. Okay, let's flip back to Khaled and take a look at what we're doing. This is all good. Okay. So you were using the axis equals 1 trick. Wonderful. And you had a plot, exactly the same structures you had before. You've added in something that Omid did not. You showed the error bars using the standard deviations. How did you go about actually creating these little vertical lines?
Yeah, so basically I used that function that I got from the documentation, x error bar, and then I just plotted the variables parameters there.
Okay, so this is exactly right. Well, almost exactly right. Okay, so I assume you've done some science, right? When we talk about an error, what's the error in? Or the variation, the standard deviation, right? You're taking an average, you're taking a standard deviation of a bunch of measurements. Do we have variation in the levels?
Yeah, it's probably the variation in the levels because it's the bar that's like going up and down there, and in some places it's like higher, in some places it's at low. Probably it's the variation in the levels.
Okay, that's what your plot is showing, but that's not what the data is about.
All right.
The data is at a fixed location, a fixed depth. But you're taking that measurement at different places and at different times. And so there's variation in the temperature and the salinity and the pressure at any particular depth because of what time of year you're taking the measurement or where you are in the ocean, right? And I'm going to go back to this graph up here that you drew. Do you see how each one of these lines has a certain characteristic width, right? There's a lot of scatter in temperature. There's a lot of scatter in salinity. There's very little scatter in pressure. It's the width of that scatter is what you're measuring with standard deviation. It's how wide the scatter is. So I would suggest, we'll just load this here. What you really want is not T min levels T standard. You want to set the X error. See that?
Yeah.
That's it's not an error. You're using an error bar to represent the standard deviation of a mean. So this is the mean, and this is the standard deviation of the mean. And you can sort of see that this shape is basically capturing the amount of variation of these curves. So these curves have a shape, and they have a typical size, a typical width, right? That's what this is saying. It's saying, as you're in the top part of the ocean, you got a lot of variability in the temperatures. But as you go deeper down, it really doesn't matter where you are in the ocean. The temperature is almost always the same. There is practically no variation of pressure.
Right.
Okay. As you go deeper, there's almost a one-to-one correspondence between levels and pressure and levels. So this is an invertible function. Right?
Makes sense.
Okay. So I understand that the science is not, you don't do oceanography, you don't do environmental science, but general data manipulation, right? Means and standard deviations. Okay. Right. Okay. And now you're taking the mean at each date. I like this a lot. And you're just not done. You stopped. Kelly, do you want to finish off that assignment 7?
Oh yeah, I was struggling to complete this particular lessons too. Yeah.
No problem. I will let you finish this off, and we'll just take a look at Omid, see if he did it. Yeah. Okay, now look at this. Oh, interesting. This is not a consistent way of looking at the data, only because you've established in your previous plots the vertical dimensions on the left. So here you flipped it around and you put the vertical dimension on the bottom. Yep. But that's fine. I understand why you did that, because you were trying to get the error bars to go in the right direction. Right, Omid?
Yep.
Yeah, okay. So the solution as before, you'd want to use horizontal bars, not vertical bars. If you want to do it your way. Yeah, okay. You did this thing, and let's just take your plot here. So now what we're doing is we're looking at average temperature as a function of time. So what's happening to the temperature over from November of 2013 to May of 2015? What's happened to the temperature?
It's decreasing apparently, yeah.
Okay, so now I'm going to give you a bit of a science thing. This is November, okay? So this is the, why do you think, and this is a science question. Why do you think the temperature is changing as it goes from November of 2013 to May of 2014?
Well, it depends on the pressure, I think, and salinity. Yeah.
No, because I'm just talking about the temperature. The temperature is independent of salinity and pressure. The pressure goes from 10 degrees down to 6 degrees. So it's got cooler. Why do you think that's happening?
Oh, it's just because of changing the seasons, yeah.
No. Because if it was the change in the seasons, I'd expect that summertime is warmer. Okay. So the trick is with these data is it's not just when the data is taken, it's where the data is taken. So in another plot, you were asked to create a scatter plot of the Argo float data. Okay. So in this plot, what are you looking at?
In this plot, we are going to see the amount of changes here.
Okay, so what you're doing is you're plotting the position of the observations. What do the colors represent?
Well, the colors shows I think the positions, yeah, the position, latitude and altitude.
No, but position longitude. Is showed by latitude and longitude.
Longitude, yeah.
Right. What's the color represent? And you wrote the code.
Yeah, the color represent the date.
What do the colors represent?
It shows date, and based on the dates, we are seeing decreasing in latitude and the position, decreasing in latitude and longitude, I think.
Okay, so I got a question for you. Which one is the first observation? This purple dot or this yellow dot?
Well, I think maybe the purple one.
How do you know that? Another way of saying is what's your plot missing?
Not exactly know about this.
Okay, so what you're missing is any scale or legend about what these two colors represent.
Yeah, right? Yeah.
Okay, so to get that information, right? We typically would add in a color bar.
Yeah, the color.
Now, when we add in a color bar, it indicates that the dark blue is the small number and the yellow is the big number, right? So I agree that this is the first observation and this is the second observation. But what do these numbers represent? These are weird. I know what they mean, but do you know what they mean? This represents the color. The color is a number? How is it that these numbers are becoming 1.37 times 10 to the 18? What's going on here when you plot this data?
Maybe I didn't just exactly color the position based on the color, you mean?
What you did is perfectly right. You're coloring based on the date. What I'm trying to get you to do is understand what you're looking at, okay? When the colors are assigned, so colors, numbers are assigned colors, right? On a color bar. So you're going from dark blue to light yellow. So that includes, it means increasing date. But why are the dates being mapped to these funny numbers? I'll pick out a certain date. Here's a date, okay? The date is, whatever that is, July 2012, right? Do you remember how we learned about representing different data types? This date is encoded. It's encoded as the floating point number 1.347221856. Actually, it might even be an integer. Yeah, it's an integer. This time is being encoded as this information right here. Okay, and the next time is being encoded as this information right here. These are what these dates represent. And so this is an important thing about representing data in memory. What do you think this number refers to? So if this date corresponds with this number, and this date corresponds with this number, what does that date mean? What does this number mean?
Well, it is the position, I think.
No, it is not a position. Okay, can you see how the 0 1920000 is the same as this thing.
Yeah.
Okay. And the 9904 is the same thing as this bit.
Format, Professor?
It's not a format. It's not encoded.
Okay.
Right. But 134099, that doesn't look like anything like 2012.
Yeah, it is the concat of longitude and longitude and altitude.
No, it is not. It has nothing to do with latitude and longitude. Okay, it's just, remember, this is just the date. That's very different than the latitude or the longitude. They're separate fields. That's not the same data at all. Okay, so as you are learning any of these things, take the time to learn about what these things are. So a date time 64 is a data type, okay? And here's the documentation for it. A date time is a 64-bit integer counting from 1970, January 1st. So what this number is the number of nanoseconds since January 1st, 1970. So in the computer world, January 1st, 1970 is the beginning of time. Negative numbers for before 1970, January 1st, positive numbers for beginning after that. So what we're looking at here is the number of nanoseconds since January 1st, 1970. Does that make sense? I'm just looking for a yes or a no. So typically when we're doing these dates, what we can do is, so a date times 64 is the number of dates since a certain day, right? So what I can do is I can put in here 2012 0101, and now these are the number of nanoseconds since the 1st of 2012. Well, yeah, a nanosecond is 10 to the minus 9 seconds, right? So this is how many seconds it's been since this date. You know that there are 36 or 60 seconds in a minute and 60 minutes in an hour. So this is how many hours all the way through the day. This is how many days, right? So you could sort of think these as being a count now in days. So day 200, day 300, day 400, day 500, day 600, day 700. So this is one way of starting to interpret that data. If you want it in years, right? Now these are years since here. So there's a 2-year record of data.
Yep.
Anyways, just talking about the data. Okay, so that's plenty. And the example is not on oceanography or climate science. It's about the data types and trying to represent that. That's tons for today on this. I will pick up 2 other people on Thursday and we'll do number 2. So thank you very much, Khaled and Omid. I'll let you off the hot seat. I appreciate using your assignments as a focus. What I'd like to talk about now is some of the things we are beginning to address in this assignment, which is how data is actually represented on the disk and how we load it up and work with it. All these fields of science use data, and we either produce data, we transform data, or we read in someone else's data. This particular data has been given to us in an NPZ file format, okay? So when we're dealing with an NPZ file format, it's a certain way that data has been stored on the disk, and we use a piece of code to load it in and make meaning out of it. When you're talking about data formats, file formats, there's 2 ideas you can think about. One is how the data is actually laid out on the disk, what the storage model used is. And then there's sort of a higher level, logical level, a data model, which explains what the data represents. So when we take a file format like an NPZ, the data model, the logical layer is the fact that the data can be thought about as a T array, a P array, an S array, a latitude array, and a longitude array. The data types of each one of these things, we talked about data types, okay? Temperature is a float 64. Levels is an int 64. Date is now I know it looks strange. It's a string of nanoseconds. This is a date time 64 as its data type, right? So these are the data types. What these names represent and what data type they are and how many rows and columns, that all is part of the data model for this format. An NPZ actually has a fairly simple storage model. And I want to talk about that for a moment just so you see what's going on. So let me just, what's the easiest way of doing this? New terminal. I need a terminal. Okay, this is open just a terminal to where we happen to be. So I'm inside this directory and there's a few files, right? So we're taking a look at this. Here are the directories, both Omid's and Khalid's assignments and this NPZ float. Now, if someone was to hand you this file and say, open it up, read it, and you hadn't done this assignment, I don't think anyone in this class would know. I know what an NPZ is. It's not a file format that you're familiar with seeing. It represents a compressed NumPy file, and you access it with npload and npsave. That's how it works in terms of creating the file. But it's a specialized file format for Argo data. This isn't the only way we store Argo data. There's other ways of storing it. But I want to talk about the difference between a storage model and a data model. So the data model is what arrays are in there, what are their names, what are their shapes, what are their units. Then at a lower level, there's how this thing's actually stored. Files typically are described by something called their file format, right? So when I look at these files, I've got 1, 2, 3, 4 different file formats, right? And you might have been trained that IPYNB, that represents a IPython notebook file, a Jupyter notebook file. MD represents a markdown file. .txt represents a plain text file. And an NPZ represents a NumPy compressed data file. In the Windows world, these extensions typically have meaning in the sense that if I load it up and I double click on it, what this extension is going to do is tell me what application that I want to run. I'll just jump over here to a file explorer. Okay, and I'll just go to my downloads directory because that'll give you a good snapshot of everything that's inside my directory. And my downloads directory is just a bunch of stuff. You know that what a thing is doing is it looks at the extension, and then the extension tells it what type of file it is. Okay, so the way that Windows and Mac OS X and those kind of languages are doing is they look at the extension, and then that's telling the operating system what type of software I want to use to open it up. So if I want to open up an Adobe Acrobat PDF document, it gives me the little icon on a PDF. It'll launch that application. If it's a Word document, so here is a Word document. How does it know it's a Word document? Because it ends with the extension .docx. That is a way that languages like operating systems like Windows use to figure out what kind of data type it is. If you change the extension for Windows, it gets confused right away. So let's just take, I don't know, let's find, here's, I don't even know what these things, I don't know, I want to find something which is not like personal. You don't need to see my tax returns. Okay, well, here we go. Here's an MP4 file, okay? So this is a little video clip that I'm going to show later on today. It's an MP4 file in the sense that if I was to go to the command line, so let's go to the command line so we can see what's going on. So I'm going to go cd slash MNT C users J Monroe downloads. Okay, so this is the directory of all those files. And one of those files in there is CMC6950 07 MP4. Okay, so it's a movie, right? Now, the operating system recognizes what kind of file it is based on the extension, right? And that's why you're getting the word MP4 file and a little icon. And why if I double click on something, what opens up is a player and you get to see whatever video clip that this is. If we change the extension, SC6950, if I change the extension, 6950, wrong extension, okay? If I change the extension, can you see what Windows has decided this file now is? Can you see that there's no icon? It's now thinking it's typed wrong extension. And if I double click on it, it's going to say, I don't know what to do with a wrong extension. It has no idea what to do with that particular file. The actual content of the file has not changed. So the file name is something that some operating systems use to just sort things up. They don't actually describe the data. The data can have any name you want, and it still will be an MP4 file. How operating systems like Linux decide that a file is one file type or not is they use the command file. And what file does is it actually goes into any sort of file and looks at the actual contents of the file and decides what kind of file this is. And you can see that when I apply file, which is a command line argument, a command thing gives a file name, it says, you know what? This thing is a piece of media, and I can see that it's been encoded with the MP4 codec. I know what this thing is. I'm not dependent on the extension. And so files have an inherent structure to them independent of their name. So here's one which is a PNG file. You might assume that that PNG file is a image file if you're familiar with it, but there's actually no need to do that. There is inside all these binary file formats certain header information that lets me figure out what kind of file this is. It's a portable network graphics file. It can pull out this kind of information. File is a really cool helper tool to help you figure out what a file actually is. Okay, so let's go back to here. Okay, so again, here's all of the files in here. Let's figure out what file type a notebook is, or an MD is, or a TXT file is, or an MPZ is. If I say file .ipnb, it says, you know what? That is a text file encoded with UTF-8, Unicode, with very long lines. As far as a file, its storage model, it's just a bunch of text. If you were to take a look at that text, you might see some structure. But as far as the storage model, it's just a flat text file. In fact, a readme.md is a Unicode text file. Now, there's a little bit of things with text files. Text files can have different terminators at the end of lines. They can have just line feeds or control line feeds. And this one has control line feeds. So it's a slightly different file format, even though we interpret the data inside of it. The data model here to be marked down and here to be the file format for Jupyter Notebooks. Let's take a look at this TXT file. It is a TXT file, but really it's just ASCII text. So this file is encoded not with UTF-16, but this is encoded with the ASCII encoding for this file, okay? So what I'm trying to get at here is the idea of a storage model, how the file is actually represented at sort of the binary level, how it's laid on the disk. These are all text-based files. They all can be read as characters in, characters out. It's quite different than this file. This file though we might interpret it as an NPZ file, is actually a zip archive. So even though it doesn't have the extension zip, turns out it's just a zip file. In the sense that if I was to rename this thing to argofloat.zip, okay, so that it looked like a zip file, I could unzip this file, and you see what's inside of this file? s.mpy, t.mpy, levels.mpy, lawn.mpy. Those are all the keys all the way through. So this file, npz, the entire storage model is just zip, as in compressed file zip. And what they do is they just give the name of each array, and then the extension is an NPY. So this is an array, this is an array, this is an array, this is an array, this is an array. Now, if we actually go and look at each one of these files, this is a file format called a numpy array. So this is a binary file that needs to have numpy as a library that opens it up. If I try and open up this file in a text editor, you just get garbage. And that's because the data is encoded in a binary sort of way. The way that an operating system knows that this is a numpy array version 1.1, it's actually looking at the first 4 characters of the file. You see this bit right here? These right here, these characters right here are called the magic codes for a file. And literally, they're called the magic codes. Every file format, the first 4 characters, there's a standard on what is this file. And people document these things. And usually the first little bit of a file tells you what's inside of here. So it's saying this file is going to contain a bunch of floating point data that's 8 bytes per floating point. It's in the Fortran order, which means that columns come before rows. And it's a 78 by 75 array data. From here onwards, it's just straight up binary encoding. So every 8 bytes represents one number. So this is sort of the low-level storage model for these files. And there's a higher level data model, which is used to how these things are put together. Okay, the reason I'm introducing this is I want to talk about data models, storage, and input-output broadly as a theme, as an idea all the way through. So is this clear what we mean by a file, like a storage model? Like how is it actually represented on the disk? On the disk, it's represented as a zip file. That's the underlying storage model of the NPZ file format. The underlying storage format of a readme.txt is just lines, right? It understands a line of text. That's how it's sort of done. But it has a data model which adds how these things are all put together. Incidentally, this assignment7.ipynb, you might actually recognize this file format. We're calling it an ipynb because it's clear that this is a file that can be read by Jupyter or Jupyter notebooks. But you might be familiar with this file format from other programming you might have done. Does anyone know a file format that has curly brackets, colons, square brackets, and commas?
That's JSON.
JSON. So the lower level model of Jupyter IP NB files, even though Jupyter considers it to be a certain something, what it does is it serializes the data into JSON, and then the JSON file gets saved as a bunch of text files. So the way that this data actually got saved is a Jupyter notebook object in memory got turned into JSON, which is just JavaScript object notation. It's this sort of way of thinking about things as dictionaries and lists. And then that got saved as a file in a certain storage model, in this case, text. You don't have to store JSON as text. There's other ways of storing the file. You could store it in a database that understands JSON entries, right? Some sort of document the database out there. But that's the idea of these models. So within different scientific disciplines, there are different file formats and storage models that come out. And so what I want to do is talk about these broadly. And here we go. Okay, so what I've introduced so far is the idea that we're talking about input and output, right? Saving things to a disk or getting things from a network. You have to understand or be thinking about what file formats are involved and how is that data actually stored. And this helps you understand how much work is going on behind the scenes and how it's put together. So we talked a little bit about these magic codes, just a way of figuring out what they are. Sometimes we talk about a file format being how it's stored, like a zip file, but we also talk about a data model like Python notebook files, meaning how the file, what the file represents, what its data structures are. And both of those two words are encoded in the file format. So when someone says the file format is a text file, that's really only telling you the storage. If someone says it's a notebook, Jupyter notebook file, then they're telling you both the data model and the storage model involved. So just to drive the discussion, what I did is I just took the list of possible topics for the projects. And we're not going to do all 24. I spent like half an hour just sort of looking at each package, taking a look at what kind of files are involved. And then I went to the next one and I went to the next one to motivate a discussion on what kind of file formats and types are out there. And I did it for like 10 of them, and then there's a lot more. And I'm just using this as a launching pad for a conversation we can have about scientific file formats and data storage, some of the concerns, some of the caveats, some of the warnings about it as we work through it. So the details are going to be domain specific, right? If you're an astronomer, you're going to use a different set of files than you would if you were an oceanographer, which would be different if you were a high energy physicist, which is different than if you're a bioinformatics person, right? Every discipline has their own files. When I talk about file formats, at some level, you might be familiar with files that you see in your application, right? We talked about like PDFs and Word documents and Excels and image files, PNGs, JPEGs, GIFs, and things like that. Different video files, MPEG 1, MPEG 2, MPEG 4, and there's 30 or 40 or 50 different video formats. That's one kind of way of thinking about kinds of files that you typically have in an office environment. What I want to talk about is files you'd encounter in a science environment. And just to talk about the differences in there. So let me see who I got actively. Why can't I make that bigger? I'm just trying to see if who's on this call and whether or not anyone's gonna ever chime in here. You are welcome at any time to sort of ask a question, or if something I'm talking about strikes a chord and you're like, I'd love to know more about that, speak up. Otherwise, or drop something in Slack. I'll try and keep Slack open here on the side so that if you do want to interrupt me, I will notice that there. Or just turn on your mic and overdo me, or I'll just talk for 45 minutes on file formats and storage models and stuff that I think is cool. Okay, first one. So I just went down the list as a snapshot of some of the scientific software that's out there. And the first one on my list was a Python gamma ray burst analysis package. So we're in the domain of astrophysics, right? So we put telescopes, we look up at the sky, and we take measurements. And as you might be familiar with, telescopes look at a whole bunch of different spectrums of information. They don't just look in the visible spectrum, they look in the infrared, they look in the ultraviolet, they look in the X-ray band, they look in radio waves, they look at gamma rays, they look at all sorts of frequencies, and the telescopes pick up information at all those different things. Telescopes have been collecting digital versions of their information well, for more than 40 years at this point, right? astronomy is one of those big data fields that capture enormous amounts of data. You might be familiar with the Sloan All-Sky Survey. Okay, so here is a project which basically they're taking telescopes and they're trying to look, well, everywhere. They're looking like up, down, left, right, all around our ocean, our Earth, at everything that we can see. And so you can go and you can take a look at this data set. Okay. The Sloan digital release, let me see if I can find a number in it. It's looking at data which contains both images and then spectra, basically like what kind of chemicals are involved, right? That's the data for it. When you actually go to get the data in astronomy from the Sloan Digital Sky Survey, one way of getting that data is to go to a web browser or what's called a file transfer protocol server, an FTP server, and sort of just find the file. So if I go to the Sloan Digital Sky Survey, I can find the file, and there's a number of instruments that have downloaded that data, and I can find some of the data. So here is some of it. And the data, often for astronomy data, has this file type. You see the FITS? Okay, that stands for Flexible Image Transport System. Okay, so it's a file format which has been developed in the astronomy community for taking pictures that you would get from a satellite, but also data that would include things like the spectrums that you would measure through a spectrometer, looking through them. So that's the actual data. Now, in terms of how much data we're talking about, when you talk about how much data is in this thing, so the camera data, right? Because of course telescopes have cameras. The data itself for just what the camera's on, that's just like five gigabytes. So, you know, like one movie. The spectroscopy files, well, that's 21 terabytes, right? But you can imagine having 21 terabytes sitting in front of you. That's not ridiculous. Just have like what, 5 hard drives, right? That's all the data from this data set. You can see that the Sloan Digital Survey as a data set, okay, is probably 40, 50 terabytes of data. So the data itself, what's in it are thousands and thousands of these FITS file formats, okay? So if I go through here and I look at any one of these pictures, I'm betting that it is oh, well, this is interesting. It's a fits.bz thing. Okay, so here's something that normally happens. Here's a file. This is its sort of data model, storage model, and then it's got another extension. We talked about zip. Do you know what a BZ2 is? Well, let's take a look at it. So copy link. I'm just going to jump over here to a terminal. Whoa, scroll down. I want smaller so I can see things. I'm just in some old directory where we can see what's going on. I'll use that same assignments directory because I got some stuff. I'll do a wget of that data. Okay, so I am downloading a particular image from the Sloan Digital Survey. So there it is. This is just one snapshot, and it's 2 megs. Okay, what kind of file is this? Again, this is where file becomes useful. You can see that it's bzip2 compressed data. So zip is a file compression algorithm. bzip2 is another file compression algorithm. So if we want to unzip this thing, it's possible. No, unzip doesn't work. BZ. Okay, to uncompress a bzip file, it's just a different algorithm. We use a tool called bzip2. And what that's done is it's taken the file and made it, it used to be 2.9 megs of data, right, when it was compressed. We use compression to reduce the amount of space disk files taken up on the disk, or to reduce the amount of data we've got to transmit over the wire. If I uncompress that file, you can see that the file is actually 12 megabytes of data. So compression on these FITS files has been about 4 to 1, right? The compressed file is about 25% of the other file. So often data, as it's on disk in archives or as it gets transmitted to you over the network, it's compressed. This is an example of what's called lossless compression. I can always go from this file using the bzip2 algorithm back to the compressed version and vice versa. I've lost no data. Zip is another compression algorithm which is out there that is lossless. You don't lose anything in the compression. The way that it's achieved this is, my guess, within this file, there's a lot of repetition. There's a lot of byte sequences which appear more than once. And the algorithm has said, you know what, rather than having this string of 300 bytes, I'll just represent that with a short indicator and say that indicator that represents that short bit, and you get a compression algorithm. I'm not going to go into compression algorithms, but it's a way of storing that data. So you can see that the data has increased by a factor of 4 if we didn't use compression. I'll go back to the fact that the Sloan Digital Archive survey is 60, 70, 80 terabytes of data. If they didn't use compression, then it would be 240 terabytes of data.